Okay. Thanks everybody for your patience with the technology. Of course, the first time doing this, there's going to be a few little bumps. But I'm glad that everybody is able to be here. So I want to say welcome from my side as well to the first installment in the Lamar Institute lecture series. What we're going to be doing this semester, we're going to be meeting on Fridays to talk about research developments going on in a wide range of different areas of machine learning and artificial intelligence. And all of these are areas in which active research is being conducted at the Lamar Institute for machine learning and artificial intelligence. Now, since the institute itself is bilocated in Dortmund and in Bonn, the lecture series will also be bilocated. On some days like today, the lecture will be given live in Dortmund and streamed here. On other days, the lecture will be given live here and streamed to Dortmund. If the technology works, we should all be able to see and hear everything and participate in the discussion. So that should be no problem. Some days, though, we might actually bounce back and forth, have half in Dortmund, half in Bonn, if we can achieve that. Okay, so if you found the lecture today, that means you already probably have a source of information about the schedule or when and where the lectures will be. If you haven't found a source, come ask me afterwards. I can point you in the right direction if you're in Bonn. If you're in Dortmund, then you can ask Vanessa Fava over there about where you can find out about the upcoming lectures. And if you have any other questions, just grab me or Vanessa after the lecture today. So let's just jump right in. Today we're going to be starting with the research area of resource-aware machine learning. First, we're going to hear a presentation, a kind of overview of this research area from Professor Jianjia Chen at the TU of Dortmund. And then we'll be hearing a research presentation from Dr. Sebastian Buschjäger, who's going to talk about some of the challenges of bridging algorithms and hardware that fall into this area. So with that, I'll hand it over to you, JJ. Please go ahead and start whenever you're ready.
Okay, thanks, Brendan. So my name is Jianjia Chen. For those who have known me, many people call me JJ. So today I'm going to talk about the resource-aware machine learning in the context of Lamar Institute. And this is also the first lecture of the lecture series. I will take the advantage to shortly introduce the Lamar Institute as well. So this is the Lamar Institute. We are located in 3 locations, Bonn, Dortmund, and St. Augustine, involving 2 universities, TU Dortmund and University of Bonn, and 2 Fraunhofer institutes. One is in Dortmund there, Fraunhofer Institute IML, and another is in St. Augustine, Fraunhofer IAIS. We have an updated number of 45 plus principal investigators. So those are professors in Bonn and in Dortmund. Okay, so the Lamar Institute for Artificial Intelligence and Machine Learning focuses its research on this triangular AI, looking at the intersections of data, knowledge, and context. You would listen to different research areas, how we actually integrate our research and also education activities into this triangular AI. And you can see that those are relevant to machine learning and artificial intelligence in different regards. So we have 5 fundamental research areas in blue and 5 application areas in yellow. Today, we start with resource-aware machine learning. Next week will be trustworthy AI. And I don't know the rest of the schedule for the semester. One important thing of the Lamar Institute is not only to look at the AI itself from computer science perspective, but also to utilize the machine learning algorithms in different application domains. Application domains include physics, life science, and also in the industry and production, specifically with Fraunhofer IML for logistics and planning. And back to the time we designed the research focus, we also had a natural language model, which has now become very popular due to the boost of ChatGPT and the corresponding chatbots that you can find also nowadays. For the fundamentals research areas, we also look at the further topics like hybrid machine learning models. So that means that you have different machine learning models that could interact with each other. Embodied AI specifically for robotics, which I'm also part of, and the human-centered AI, if AI are used in human in the loop. Okay, so one of the missions with Lamar has is to do not only research, but also education. So you can find all the education programs. And today we are in that umbrella of university education. So it's a dedicated machine learning colloquium on the way. And this is one of them is to have machine learning courses for different master students in different programs. If you want to follow us in terms of education and also activities, there's a machine learning blog you can find here. And we also have quite a lot of news updates from LinkedIn and corresponding activities. I should have a barcode here to QR code here to allow you to take a look. So without actually spending too much time into advertisement, I would like to talk about resource-aware machine learning. I'm going to take a look of the high level. I didn't expect that we are going to talk about the research results we have because I think we don't have that today. We are talking about the fundamental issues, why we need to look at the resource-aware machine learning. And what I'm going to talk today is very basic. And you would probably sometimes also wonder, why can Professor Chen and Sebastian Busch-Jaeger publish those results? Shouldn't they be known already in the bachelor study program? In some cases, some results were actually published because we gave a first semester lecture, and the output was the extension of the materials I used in the first semester lecture. So we're going to talk about very basic understanding of resource, in our case, computers, and very basic machine learning mechanisms. How do you actually put them together? Okay. Of course, you can make those things much more dedicated to look at more fundamental models or more advanced questions. But today we focus on more general concepts. Why do we do resource-aware machine learning? So this resource-aware machine learning area is coordinated by me and Sebastian Busch-Jaeger, who is going to give the second part of the lecture. And we also have quite a few researchers. Two of them are sitting here, and there are others somewhere. I don't know whether they are in Bonn or not because I cannot see any. So it's about resource awareness, right? So now when you think about how you ask a machine learning algorithm, and you have to deal with the resource you have, then at the all of a sudden you will realize the fact that, do I have sufficient money to buy GPUs? Can I buy GPUs at all? Does NVIDIA want to sell me their GPU? It was like a very bizarre question you would ask at the beginning. But nowadays, it seems like you are not a loyal customer at all. Why do they want to sell you those GPUs? Right? It's a very strange question, but we have the question. Or you have some machines that you don't use at home, like a PlayStation 4, because you have PlayStation 5. Can I run some machine learning algorithms on my PlayStation 4? And you will say, oh, there's no CUDA. Everything I have is with CUDA. How can I actually understand? How can I actually run those machine learning algorithms on the old-fashioned systems? Yeah. So what do we do is to actually cover the spectrum of resource awareness and machine learning algorithms and artificial intelligence. So this covers, for example, model deployment. How do we compile a model that was originally designed for a high performance computer into an edge device? Okay, or from a new library to a library that a system that doesn't support those new libraries. Okay, that's the first one, model deployment. How can we train the model to be aware of the limited resources we have at hand? Can we reduce the energy consumption, memory usage, and can we take care of the time that we have to do the inference? What happens if I need to deliver a result within 1 second and the inference pipeline must be interrupted to deliver the result, even if it hasn't finished its completion yet, right? How do I do the online learning? How do I actually learn the model on the proactively and reactively on the way? How do I benchmark and report the different results that we have if we have different resources? Should I focus on energy efficiency or should I focus on the execution time and the energy memory consumption? We also look at the normal hardware and applications. So those are more relevant to our other research domains that we focus on models that you don't use the von Neumann model anymore for inference or training. You don't you use the memory directly for computation. Or what happens if we have quantum computers? Can we do quantum machine learning directly in a more efficient way? Those are the topics we have. Today, we talk a little bit on what our basis is. So why do we have to look at resource-aware machine learning, right? If we look at the simple scenario that Tesla cars using deep learning for image recognition and steering, have you thought about the energy consumption it needs if we all have Tesla cars? I don't force you to do Tesla cars, but if we have a lot of Tesla cars on the street, let's look at what happens. So the report shows that the customer chip Tesla has is 57 watt. And let's assume that you just do this for the time you drive. How much time do we drive a year? So all cars in Germany combined travel 630 billion kilometers in 2018. So we still don't know how many hours we have, right? Let's convert that to the amount of time we drive in Germany. So the average speed of personal cars, I just checked my car last week, only between my home and here. So it's actually only 45 kilometers per hour, but apparently it's close to this. If you take this into time that you have and put the power consumption you have together, if you use autopilot in all the trips, will require you almost 0.7 terawatt hour. And this is not too much, right? It's not just, it's basically just the largest run-of-the-river hydroelectricity plant in Germany that produces roughly this amount of power. So you use the you use the largest plant only to power the cars, right? So what happens if we can reduce the energy consumption by a factor of 3? Then we can actually reduce the energy supply that's needed over here. So the key part is that if you look at the energy consumption or the power consumption the chips have, 57 watt is not even a lot when you look at NVIDIA GPUs nowadays. But it's actually a lot if you compare that to your phone, right? If you need to supply your phone with 70 watt, then you would probably have to charge your phone, I think, in the hourly basis, right? Okay, so let's look at another problem, which is relevant to sustainability. So if we look at the resource we have invested to produce a phone, how much do we need? So let's have a look at the iPhone in that case. In this case, the production of the iPhone takes some amount of carbon dioxide, and the transportation also takes a certain carbon dioxide, right? If you use the iPhone only for 1 year, you are basically only contributing the usage of the production and transport by only, my calculation is not that good, 6% to 7%. If you use that for a second year, 11%. sorry, 12% to 14%. If you use that for 10 years, you are still worse than the amount of carbon dioxide that has been emitted for production. How much time do you use for your iPhone? I think the typical view is roughly 3 to 4 years, right? So we are in the range here that most of the time your devices are still useful, but you just don't use them anymore. And it's even not break even in comparison to the production that it has. So if you look at the game consoles, we have millions of game consoles that stay at home without any purpose. You can use the game consoles for inference, for the things that you can do at home. You probably don't need to buy the new devices at all, right? So the question is like, you want to have a fast system, whether you always need a fast system or not. If you can use the old device, which is nowadays still very fast, to do the inference you need at home or for your daily business that doesn't require you to use a high performance GPUs, how do you actually achieve that, right? So we have to run algorithms on those hardwares to be aware of the old resources. So not all the hardwares that you have at hand has CUDA. Now all hardwares that you have at hand would have the latest libraries you have. How can we actually develop machine learning algorithms that are not only for the new customers, but also for our environmental sustainability? This is what we want to do. And this is the whole motivation of resource-aware machine learning, right? So let's look at the resource we are looking at. If we look at the energy consumption, so energy consumption is the power multiplied with time. If we want to reduce the energy consumption, we can reduce the power, or we can reduce the execution time, right? So if we look at the hardware, then we have different hardware. I'm from embedded systems chair, so for me, those are the hardwares we look at, right? So Arduino to Apple, those are super powerful devices. If you look at the flash memory that it has and the SRAM that it has. More importantly is that we talk about Tesla car, which consumes 57 watts. And now the old Apple phone has only a few microampere. Of course, you need to multiply that with the power consumption, you get a corresponding energy power consumption. But looking at all the devices you can see here, they consume very little amount of power consumption. Let's say if you multiply with the voltage here, I think it's roughly 12 volts. For some of the devices, you get in the range of a few milliwatt to a few milliwatt to one or a few watts. Huh? This is much less. If you look at the operations we can do, in this case, the energy consumption per operation, if you can use the integer operation points, for example, the 32-bit integer at operation, it consumes 0.1 picojoule. In comparison to 32-bit floating point for addition, would consume 0.9 picojoule. This is 9 times difference. Right? So if you have a way to use the integers instead of floating points, it would be better to use integers, right? So when we can use integers over floating points, we should use the integer points. And if we look at the memory access, when you have a cache hit, the energy consumption is between 5 picojoule to 50 picojoule. But if you need to go to the dynamic DRAM to access the data, it's another level of energy consumption. So all in all, we should try to understand the computer organization to actually reduce the energy consumption that we have to consume, right? This is also similar if we look at the devices we are looking at. This is now with the power consumption we can see. If we have a microcontroller, which is our favorite in my group, MSP430. We have plenty of them in my group. It consumes only 5 milliwatt to 50 milliwatt. This is like 1,000 times less than the Tesla chip, right? Or much more than the NVIDIA. We are not stating that we can do the same performance, but if we are able to run a neural network on those microprocessors or microcontrollers with similar performance, then we are much energy efficient. Whether we can achieve that or not is another story. Sebastian will talk about that later on. If you leave this compared to i7, which you have in the desktop, this is a drastic less power consumption when we are talking about. Okay. Yeah, so I'm not going to talk about neural networks. At the beginning, Sebastian will follow that. I'm going to use the decision trees to give you an example how we can execute decision trees efficiently. So decision trees are trees that make decisions for us, right? How do we make how do we actually organize a tree? We start from the root to compare an input value, in this case, the first entry of the input, whether this input is less than or equal to a certain threshold. If yes, we take the left-hand side. Otherwise, we take the right-hand side. You can also organize that in different ways. And then if we are here, if x0 is less than 1.0, we will come to this point, x1. We check whether x1 is less than or equal to 1.0. If yes, we go to this point. If then again x0 is less than or equal to 0.4, we would classify this item as number 7. If this is x0 is more than 0.4, then we classify this item as 8. So in fact, you can make a lot of, you can use decision trees to make a lot of automations. In my group, we use decision trees during COVID time to decide whether we go to Mensa or we go to full facultet for our lunch. Or you can make anything you want in that decision, right? There's one assumption in those decision tree. You would always start from the root and go to a leaf with to classify one data item, right? And more important thing is that when you use that with more decision trees, you can have a forest, and then you can make the so-called assembled decisions. So basically, you take a majority vote after that. Oh. So I said that we will talk about neural network. You will talk about the neural network. Now, when we look at the computers, it goes back to my first semester lecture, that we can have different memory hierarchies in computer systems, right? In this case, we have 2 processors. We may have local cache and shared cache, and we may have memory. The assumption is that the memory is larger, more power consuming, but it has longer latency in comparison to cache. The cache is limited, but it's faster and it's more energy efficient. And if you look at the processor unit, you have different execution units, different ALU, different execution arithmetic logic units you have, and you would have different pipelines units that you would actually have in your system. So understanding how your machine learning algorithm is executed in a hardware is what we try to do in this part. So as I said, we are going to talk about 2 basic cases. I'm going to talk about a random forest part, basically decision trees. Sebastian is going to talk about the neural network quantization and binarizations part. Okay, so now we are given a random forest. You see a few trees, right? It's a symbolic trees. And we are staying between the hardware and the models. And we want to implement the trees. And we want them to be implemented in a way that we reduce the energy consumption we reduce the execution time, and we don't change the model. Well, if we don't change the model, what can we do? Right. So let's look at what we have. That's option one. We have a decision tree that we want to implement. What we can do is that we encode, this tree, this node as a data structure, right? And in this data structure, there's a split value, which is a constant, and it has two children, left and right. Okay, so and I have an index here for the data entry. I need to look in my input. So what I need to do is to do one thing. I check whether that input I have is less than or equal to the constant I have here. If yes, I visit the left child. Otherwise, I visit the right child. Right? And this continues until I'm at the leaf. When I'm at a leaf, I just report the corresponding classification. So this corresponds to this piece of code. Very simple, right? I have this loop. If this node is not yet a leaf, so I sometimes forget that this is a hybrid. I have to use the pointers. So if this node is not a leaf, I do the comparison. If that value I have for this specific node is less than or equal to the split value, I go to left. Otherwise, I go to right. And if I'm already in a leaf node, I will just return the prediction I have for the classification. So very simple, right? I think you know how to write this program in the first semester, no matter which study program you have when you have programming course. No objection. It seems I don't hear any objection in Dortmund, but maybe it's the same also in Bonn. Okay. Now let's say if you don't know how to do program at all, what is the alternative you would do? That's pretty. Cases. Yes. That's too advanced. Before you learn cases, what else? What did you learn? You have the switch of a variable and two cases, right? Before you learn to have different cases, you have the if and else. Right? A decision tree is a lot of if else. Right? Surprisingly, we just do a lot of if else, which also works, right? Now we can ask ourselves, which one is better? Which one is faster? Which one is better? Or are they different? Let's say if I have the same tree, I get a tree as an input. I can implement the tree in this way or in this way. Because the tree itself is a constant structure, so I have the split values encoded as a constant, right? So what I can do is to just put all of them in. So I think you would learn this first as a high school student. I think my son would implement this as a 12-year kid. I think if I give him some help, he can do this as well. Now the question is which one should we use if we have a tree? Any guess?
I can guess, probably.
Yes, please.
From my standpoint, if you want expandability of our model, we should use the left implementation because it supports arbitrary number of nodes in the tree. But the right implementation with straight up hard coding constants is faster because of compiler optimizations in C++. Many of those branches would be, I guess, truncated and replaced with more efficient machine code.
So if I can repeat, the right-hand side, the if-else part, can be optimized by the compiler. So it would probably also have some prediction additional features in the hardware. So it could be faster. On the left-hand side is if-else structure. You will need to do some decoding of your data structure to the memory indirect reference. So it may be slower, right? But yes, that's the first impression we would have. Right? Let's take a closer look into this. So I have already said this. Okay, I think I don't have let me go back to this later. Oh, I somehow lost my slides. Okay, so when we do the implementation of decision trees, this is the first structure we have looked at, right? So it's very easy to implement. Your program is very small, right? The advantage is that you don't actually need to utilize you don't actually have a long code. Your text segment is super small in your program. So you basically can utilize the iCache very efficiently. But you would need to have a data access to your data array. You need to organize your data, right? And this would require you to organize your data in a data cache. And you would require indirect memory access because you have to decode. You have to refer to the node and then decode that to the corresponding data structure you want to use. Okay? So what you said is right. Now let's look at the other side, the if-else code. Right? So it's a super long code, very long. In that case, you don't need indirect memory access anymore. There's no data structure involved, nothing else except the array you put into comparison, right? The compiler can optimize aggressively. You really need to optimize the iCache because your if-else structure would like a random walk in your instruction cache. And there's no hard code. You're like jumping everywhere in your program. You don't know what you are doing, so you do if and then else and then if else, right? So you don't know whether the next one is if they're taken or not taken. You are jumping or not jumping, right? So if you look at these two programs, the first one is a very succinct code. The second one is a long program that requires a compiler optimization. But due to the compiler optimization, this could be faster. Okay, potentially. If your compiler can compile a lot of if-else branches. So we had the experience, like we had 32 levels of if-else. It's super deep, right? In the if part and else part, the compiler gave up. So it's possible as well. If you make it even deeper, the compiler could also could not do that at all. This was one of the reports from Facebook back to 2018 when they used compilers for this optimization. Okay, so what's our option here? In fact, I should go back to the slides earlier. So what can we optimize? If we look at the decision trees, we are not just training the decision trees for nothing. We are training the decision trees based on the input data, right? And there's one assumption that your decision trees would deal with similar data when the decision trees are used for inference. Therefore, we can probably try to understand the probability of our decision trees based on the training data. If we look at the training data, we know that we have a certain probability to follow a specific path. Then we can utilize the information to design our if-else structures or the access to the nodes, right? So let's take, for example, have this decision tree. The most likely path would be this 0 to 2, and then 2 to 5, and then classify with 75% here, right? Let's do the multiplication. This is 80% here. Now to this node 5, it would be 56%, and to this point would be 42%. This is like 40% of your cases. If we do it wrong, or if we do it arbitrarily, this would be the case we will see. So we have this most likely cache. Let's assume that we do an organization of our tree based on the ID. So we say node 0 is the first element, and then node 1, and then node 2, and then node 3, node 4, and node 5. We just organize that accordingly in the array that we have seen earlier, 0, 1, 2, 3, 4, 5. And let's assume that our cache 9 can host two nodes. So now we load node 0. So you have to load both of them to the cache. It's a cache miss, but it load them. And then you access node 2. It's another cache miss. And you load node 5. It's yet another cache miss. So you have 3 cache misses in your access to that data structure. But if we don't do this, instead we say, come on, 0 and 2 have 80% probability. After 0, you have very high likelihood to follow 2, right? Let's just organize them differently. I change this to an order, 0, 2, 1, 3, 4, 5 in that sequence. And then when I access this likelihood path, when I first access 0, the next time when I access 2, it's a cache hit. Instead of loading this node 2 again from the memory, it's already in a cache. So we don't actually have to access the main memory once more. So this reduces one cache miss, right? So can we utilize that? Yes, right? We can actually utilize that reference by organizing our decision trees in a different way. How do we change that? The default implementation of a decision tree is to just organize your tree according to the IDs of the nodes, which you can question who gave you the IDs of the nodes, right? Now what we say is that instead of organizing your tree based on the unknown IDs, let's try to organize them based on the likelihood of your probability. In the paper, we of course talk a little bit more details about how to do that. How do you formulate the kernel? How do you actually find the likelihood of your data structure that you can put them together? But essentially what you are doing is that you organize your if-else data structure. You organize your nodes in a tree in a different order, in a different manner. What you are saying is that originally you say if x1 is less than or equal to 1.5, do something, otherwise jump somewhere. We change that to if x1 is greater than 1.5, do somewhere, otherwise go to somewhere to do something, right? You change your if and else structure, you change the layout of your nodes in the tree. You do not change any structure, but you just change the point that you index those data structures. You already can get an improvement. How much can you improve? So the upper parts, the green and the blue kernel lines are the points that we use the native structure with a while loop. The if-else structure is the lower part, these two. If you optimize that, which is the yellow point here, the orange point here, you can already see a significant difference in terms of a speed up you can get. So now you can ask one question, wait a second, did you change anything? Technically, we haven't changed anything. It's the same decision tree. It's just a different organization of your nodes. It's just a different organization of your if-else structure. Essentially, it's the same program. It's the same tree, but you have different execution efficiency, right? So now you can also do that to actually, wait a second. So you can also see that if you look at the different structures, this is an Intel server. This is an embedded processor. If you optimize two of the decision trees, you can see that you can improve up to roughly 70% in comparison to the basic implementation of decision trees. I'm not going into the details of how you do it. If you are interested to use that, welcome to download our tool. It does this compilation automatically, right? So is that the only thing we can do? When I say that if-else trees utilize the instruction memory only, is this always true? Let's have a look take a closer look. This is a very simple if-else structure. We want to know whether this value Px of 3 is less than or equal to 1.5. Right? We got a problem now. If you look at the details of your computer structure, 1.5 in a floating point format needs 32 bits. You cannot encode a constant of 32 bits in an instruction of 32 bits. You need still the operation code and other stuff. So you need to find something else. So what the compiler does is to compile this 1.5 in a data segment, and then you do the comparison to the data segment as well. So this access of 1.5 is in fact a memory access, not part of your instructions. So again, our code is small, but every time when we need to do the if comparison, we have to look up a data. And we don't know where the data is stored. Again, the data is stored by, the data is compiled by the compiler and put somewhere, right? So what can we do? In fact, this results into, you have three instructions for this if statement, but you result in 3 instructions. 2 of them are memory access. Only 1 of them is to do the comparison and jump. Okay, so it doesn't work again. We do it out of memory access. So what we have done is that instead of using the letting the compiler store this arbitrarily somewhere, let's take the control back. So we can take the control back. What we do is that we do the encoding of 1.5 in the binary format through our toolchain. It's still 1.5, the same value, the same thing, but we don't let this to be done by the compiler. Instead, we push this constant, 1.5, into our instruction. So it's now an instruction. So we force this constant to be encoded as an instruction instead of letting this constant be stored in the data segment. So we have to do more instructions. Instead of, in our optimized version, we use 5 instructions in total. In the original statement you see before, we have 3 instructions only. Now we have 2 more instructions, but we reduce 1 data memory access. Okay. By doing so, we again improve another 30% in comparison to the method you have seen earlier. Okay. So you can continue to do this. We have other means to do this. One example is that now if you see that this is 1.5, right? Originally, you compare these two with a floating point unit. Then you need to use a floating point unit for something that you don't need floating point units at all. If all the values are positive, then you can directly use the corresponding binary representation for comparison. You only need integers. You don't need floating points. It's faster and more energy efficient if you don't need that. Yes.
So do I understand correctly that then like the number is directly stored like in the instruction list?
Yes.
How does the processor not get confused by that? Like
for the computers that don't care whether this is, let's say if you store 1.5, you can store that no matter which one you use. If you store in a data segment, you still store this corresponding encoding 0x3 FC00000 in the data. I mean, at the end, it's loaded into a register as a data, right? And the data at the end in the register is the same. No matter whether you load the data from a memory segment or you load the data through your instructions, they are the same at the end, right? Okay, good. So what you're doing here is to move this constant to a register over here. So what we can do is also to change this comparison using floating point numbers to integer units, and it's also faster and more energy efficient. Due to the lack of time, I didn't actually include that in the slides. But what have we done? We started with a decision tree, which was optimized. Sebastian optimized that in his PhD dissertation together with my student, who is now an assistant professor in Netherlands. We got 30% improvement without changing any structure. And then Christian Hacker looked at the problem with if-else trees, further change the behavior of, change the compilation structure to move the constant from the data to instructions. We got another 30% improvement. And then we also realized that we don't need the floating points at all. We only need integer points. We got another 30% improvement. So all in all, we got roughly 70% improvement by just playing some computer architecture tricks without changing any structure of the decision trees. Right? So this is the best story we can actually convey. Understand your hardware, understand your program. When you don't need floating points, don't use them. When you find a balance between your data and instruction segments, try to balance that. Understand how your compiler treats your program and do the right thing, and you probably can actually improve the energy consumption, improve the execution time by understanding the hardware and software parts of your system. With this, I hand over to Sebastian to continue.